In a high-performance engine like V-engine, performance isn't just a nice-to-have, it's a foundational feature. It's not an afterthought. And while our data-oriented design gives us this incredible cache-friendly memory, our systems still have to be extremely smart about the work they do. So, how do we actually tame that beast? Let's break down the strategies.
This number is everything. To hit a silky smooth 60 frames per second, every single thing the engine does, physics, AI, rendering, the whole shebang, has to fit inside this tiny, unforgiving time limit, 16.67 milliseconds. There is absolutely no room for error.
So the real question is, how do we get from the chaotic, spiky mess you see on the left to that beautifully stable, predictable performance on the right? Well, this explainer is all about the practical, real-world patterns that let us run over 30 different systems all at once and have them coexist peacefully inside that strict frame budget.
Okay, so our first, and maybe our most powerful pattern is built on a really simple truth. Not every single computation needs 60 Hz precision. We just don't need to check everything 60 times every second. And this is what we call frame skipping. The whole goal here is to amortize that expensive work. I'm talking about complex AI behavior trees or health regeneration logic. So instead of running these heavy calculations every single frame, we just execute them once every, say, n frames. It's all about doing less work, but doing it way more intelligently.
And this visualizes perfectly how it all works. We can use the engine's timing system frame tick to stagger these updates. Just look. The AI system only kicks in every 5th frame, while the health system is running on a totally different cycle. This makes sure their heavy workloads get spread out evenly over time, which is absolutely crucial for preventing those huge performance-killing CPU spikes.
All right, let's keep building on that. Our next pattern isn't about the main game loop itself, but it's about those really critical moments during startup and loading. It's all about being efficient from the very first second the engine fires up.
This is what we call lazy resource loading. So instead of trying to load everything up front, we put off the expensive stuff. Think about decoding a big WAV file or uploading a massive mesh buffer to the GPU. When the engine boots, we just create a tiny, lightweight placeholder, a handle. It's only when a gameplay event, like an entity actually becoming visible, needs that resource, that's when we trigger the real action and do the full heavy load.
And this slide right here, this tells you exactly why we do it. This pattern isn't just some clever little trick. It's literally how we meet strict project goals. A hard target like complete engine initialization under 2 seconds is only possible because we're loading smart, not hard.
So our third pattern is maybe the most intuitive one of all, conditional processing. The fastest work is the work you don't do in the first place. This is all about completely bypassing logic that gives you zero value in the current game state. This is one of our main tools for sidestepping redundant logic. The most obvious case is pausing the physics when a menu is up, right? But it gets way more granular than that. We can disable animation updates for characters that are way outside the camera's view. If it doesn't need to run, we just skip it. Work skipped, budget saved. Simple as that. Okay, so that's great for coarse system-level skipping. But what about getting even more granular? What if we want to skip unnecessary work inside a system that's actually running right now? Well, that leads us to our most fine-grained pattern.
Meet the dirty flag. The idea is so simple, but it's totally profound. An expensive calculation, like combining a bunch of matrices, is only done if the data underneath has actually changed. We track that change with a simple little flag. If the data is clean, we just reuse the cached result from the last frame. No work needed.
And the impact here is massive. In hierarchical systems, like V-engine's TransformSystem, this means we can handle thousands of static entities, trees, rocks, buildings, with almost no CPU cost. Their world matrix is cached, and we only recalculate it if they actually move, which, for a piece of scenery, is pretty much never.
And here's the logic in a nutshell. An entity's position changes, and all we do is flip a tiny bit, the matrix dirty field, from a 0 to a 1. That's it. On the next pass, the system sees that flag, does the expensive matrix math just that one time, caches the new result, and flips the flag right back to clean. It's incredibly elegant and super efficient.
So let's kind of zoom out and pull all this together. These aren't just isolated tricks, right? They all form a cohesive design philosophy, a performance mindset that really values doing intelligent work over just raw brute force.
So here they are, our 4 key patterns. We've got frame skipping to distribute our work, lazy loading to defer it, conditional processing to bypass it completely, and dirty flags to avoid doing the same calculation over and over. Each one tackles a completely different aspect of performance. And when you boil it all down, this is the big takeaway. These patterns prove that high performance isn't just about raw speed, it's about doing only the work that truly matters. By cutting out all that redundant work, we save those precious CPU cycles for our most complex and demanding simulations.
So we've made our individual systems lean and efficient. That's great. But an engine is a symphony, right? All these systems have to communicate. So now that they're all optimized, how do we get them to talk to each other effectively? Well, join us next time as we dive deep into the internals of the job system.